So I will let Fernando then introduce the department.
Okay, so first thing is, so it's my second time in St. Petersburg. I must say that I really enjoy coming here. It was a pleasure last time. It has been a pleasure so far. I also find quite amazing to find so many people in a sunny day, Saturday afternoon. So here's the University of Lugano in a few slides. So it's located in Switzerland, just to get the first thing straight. So it started a few years ago in 2004. And it's the fourth faculty at the University of Lugano. The university is small. I think it's among the smallest universities in Switzerland, and it has only 4 faculties. One is, so there are faculties in communications, economics, architecture, and a faculty in informatics. So the general objectives of the faculty is to be international, which basically means that most of the professors, they come from different parts in the world. Also, it's true for PhD students, master students, and also for our bachelor students. So the only thing that's quite unique about the University of Lugano, the computer science department or informatics department, is that everything, all the 3 levels of education, the bachelor's, the master's, and the PhD are all in English. Even though the local language is Italian, we still teach our bachelors in English, which also allows people from different parts of the world also to go to study computer science in the first level. Interdisciplinary, so it means basically that we don't only cover computer science, but we also start widening to other directions like computational science. Innovative teaching curriculum. This basically means that there are several assistants per, so the rate of students and assistants is high. It's low, meaning that there are many assistants for bachelor students, and there's a lot of contact between students and professors. There's no distance as there are in some other institutions between students and professors. And there is a systems-oriented research, which can be interpreted in many different ways. We try to, so part of the faculty has a more systems orientation, another part has more theoretical orientation. This has changed a little bit in the recent years with new faculty members who do more theory. So here is a little bit of the numbers, just to give an idea of the size of the faculty. There are 18 professors. I think it's a little bit outdated that we are more or less like 20, I guess, or reaching 20 faculty members. There are 9 postdocs, 75 PhD students, 76 students, and 73 bachelor students. So that's what I was saying before. So PhD students, they assist the professors in the courses. There are more PhD students than bachelor students. So if you're a bachelor student, you can count on one PhD student to help you out during your studies.
This is indeed unique, right?
Yeah, that's quite unique, yes. So the other thing is, as Natasha briefly mentioned, and I guess we're going to talk more about this later, we offer scholarships at the master's level and also at the PhD level. At the master's level, there are 2 kinds of scholarships. One which is offered by the university at large, which means that it's for all the departments, and there are approximately 20 of such scholarships. So I'm told that these scholarships haven't been used actually by the other departments. And they cover the basic living in Switzerland. So it's 4,000 Swiss francs per year plus an apartment. So this is barely enough to live in Switzerland, but it should be almost possible, yes. And then there are scholarships that are granted by the department. And we have 5 such scholarships. As Natasha said, last year we had 3 master students on similar scholarships. So here the amounts are a little bit higher than for the university grants. And in addition to the master's students, we also have scholarships for PhD students. So a PhD student in Lugano, it becomes basically an employee of the university with a salary. So it's, I guess, scholarship is not the best term. And these are directly funded by the professors through department funding or research funding. And here, well, the amounts are considerably higher than for master students because, as I said, you are considered some sort of employee of the university. You also have to have teaching duties. You have to help professors in courses and so on. Do you want to add something to this?
Yes. So you're all invited to apply for master's program or for a PhD program, whatever is applicable for you. And in order to be considered, you have to fill up the application form, and you will find this form at the department's website. So there's a link. So in order to qualify for scholarships, you have to be admitted to the program. Means there will be a committee evaluating your application, which you will do using that forms I just mentioned, and then at the same time you can apply for scholarships. So it's not like us giving you the scholarships. All we can do, we can make a recommendation. So the best students who will be doing very well in our exam here, so they get these scholarships. But you have to be clear about it that you must apply for master's and PhD funding when you apply just to get into study program. I guess that's it. Other questions? That's what we are going to do. We are going now to teach 4 different subjects. So you please take notes, listen to us, ask questions, and then next Sunday we will have an exam. It will be partially written, partially oral, and based on the results of this exam we will make recommendations for a number of students to be admitted to the program, and we will make a recommendation for these students to receive scholarships. Last time we've done it and it worked perfectly
I think it was
fine.
positive.
So everything was positive, people received funding and they are quite happy in Lugano now. So the sessions we are going to teach are by Fernando on
distributed systems and distributed databases.
So then it will be my session on software verification. And next weekend you will have 2 more professors, Fabio Cristani, who is going to give you lectures on information retrieval, and Mark Langering, who is going to teach...
I don't know.
What? Who knows?
Security? I don't know.
That's a good question.
Oh, ubiquitous computing, yes, right, yes, correct, yes.
You will find out what it is about, so we probably should also do that.
We should attend to.
So, okay, an exam will be covering all 4 subjects. So we understand it's quite dense, so you really have to figure out what it's about, but it shouldn't be much pressure for you because it's all introductory level, so we are not naturally go into any details. So you just have to be able to get the ideas and being able to express yourself. It could be a good idea for you to bring your CV, your resume, by the time when we take your exam, so you actually can introduce yourself, so we know a little bit about your background. So everything will be in English, written in English, and oral exam will be also in English. I suggest you talk to professors during the breaks, before classes, after classes, if you have any questions. And that's all. So we brought some material describing the department. So all the information or all the links are here. So it tells you statistics of the department. It also describes our semesters. What's more important, there is a list of professors, all of them with the areas of their research. Naturally, you're invited to study not only with 4 people who are going to be here, but with everyone. So if you find some particular subject you're interested the most, you have to contact these people. They know that we are here and they know that we are inviting everyone to any program. And essentially for a PhD program, you have to establish a strong contact with a particular professor and convince this person that you want to study with him, and he has to be convinced that he will pay you scholarship. Okay? Are there any questions?
Questions in Russian? Not yet, okay.
Then we will start with the lectures. So Fernando will be the first to teach, and I will be back in 1 hour.
Okay.
Okay.
So let me get started here.
So I'll do this in two parts. We're going to get started today, and we'll continue tomorrow morning. If you have any questions, really, don't hesitate to interrupt me and ask the questions. And if you think you have trouble to ask the question in English, you can ask it in Russian. I won't understand it, but I'm sure somebody's going to translate it for you. So this is somehow related to part of my research. Maybe I should start by telling you a little bit about what I do. So my area of specialization is distributed systems at large and distributed databases. And we do, so I have a few people in my group, and we do both systems work and more theory work. Although I must say that most of the students I have in my group now, they are doing systems work. What this means is that in addition to proposing new things, new protocols, for example, I'm going to tell you a little bit about some protocols in the context of replication, and showing that these protocols are correct, by formally showing, by proving that they guarantee a certain number of properties that are meaningful in the distributed context. We also like to implement these systems and see how they perform in reality. Because, so this is, I think, to give you a better understanding of why you are doing this. My early research was mostly theoretical. So it basically means that I was proposing new protocols, new algorithms, proving them correct, and analyzing as much their performance as much as I could analytically, by quantifying some of their properties. For example, the delay of these protocols in I don't know, for example, number of communication steps, number of messages they exchange, or the message complexity of the protocol that has linear message complexity is better than I don't know, some exponential complexity protocol. But this is a very coarse grain. In reality, when you get to implement two protocols that had that would evaluate in the same way, according to these metrics, if you'd implement them in a real environment, they would have pretty different performance. And the reason is because usually these metrics that you can use analytically to evaluate the protocols, they are not fine-grained enough to expose all the details about the systems. And based on a few experiences where we thought that we had made, I don't know, some great discovery because the protocol had a very nice performance according to these analytics, we realized that in practice they are not so good because of other reasons that is very hard to capture in your analytical model. And based on a series of experiences of this nature, I started looking at more systems work, which basically means trying to validate these protocols experimentally. Now, this is part of the work. The other part is I still have a few students who do mostly theoretical studies. They propose new protocols, and then they try to prove them correct and evaluate using these metrics, and the work stops there. What I'm going to tell you about today is a little bit of both. And this is not only my work, so this part of this is my work. Some other is just the state of the art in the field, things done by other people. I try to give credit to people who actually did the work. And it's a tutorial basically. And it tries to, the goal here is to connect two areas that were thought to be disconnected. Actually, they evolved independently of each other. One is called object replication. So replication, as I guess, what I hope you know, is one mechanism to render systems fault tolerant, highly available. It was mostly of research interest until some years ago, and more recently it became very real. All these systems that you have, sometimes you use without even knowing. Most of the systems that actually make the internet run, all the systems that implement many of the services that are available on the internet, they heavily rely on replication. So it basically means you duplicate many of the components of the system so that if one crashes, the system still continues to run. So what I call here object replication is what was developed during many years, I guess about 30 years now, in the area of distributed systems. And I will clarify later in my talk what I mean by the area of distributed systems more clearly. So parallel to that, there was a lot of work on database replication. So database replication was a different community who was also doing this work. And they came up with different protocols, different systems. And it was believed that these two threads of research were pretty much independent, but they were tackling more or less the same problem. But they had different protocols, and some of the protocols that work in one context would not work in the other context. And what I try to do today is to show you that in reality, you don't have to look at these two areas as different things, but as two ends of a continuum. Okay? Again, don't hesitate to ask questions if there is something that's not clear. So here's an outline of this talk. I will give you some more motivation for why you should be looking at these things. And then I will spend some time explaining the model, all the assumptions that we make in order to study different replication protocols. I will then show you how you can actually go from replication protocols developed for objects or distributed systems and how you can make these protocols usable in the context of databases. I'm going to talk some time about a very known mechanism for database replication, which is called the deferred update replication, and then I will conclude the presentation. So yes.
How wide is the notion of a database in your research, in your lectures? Is it constructed by some formal definitions, or it is as wide as we can imagine?
So I have a few slides that detail the database model, which I think is going to make this more clear. So I'm going to defer the answer to your question until I get to those lines.
Could you give an example of such a discrepancy between analytically computed performance or protocol?
Yes. Let me see here. So I also have some slides that illustrate the protocol, and then once I get those lines, I'm going to show you the difference. Okay, so here is just restating what I just told you from object replication. So object replication basically means replication techniques that were developed in the context of distributed systems, the distributed systems community. And then here the second inner bullet here, is more meaningful. So I mean, when I say object replication, right, I'm really talking about non-transactional objects. This basically means if you send several requests to an object can be anything. It could be, for example, a file system, right? A file server can be seen as a big object. And your clients are accessing this file server by submitting requests to read files, to update files, to create new files, and delete files. So by non-transactional, I mean that if the client submits a sequence of requests, some of these requests may be executed, some of these requests may not be executed. But there is no notion of atomicity that groups all these operations as a single operation. Right? Each operation is submitted and it may or may not be executed. And usually there is no much synchronization between between the operations that are submitted by different clients. Now, on the other end, we have what is called database replication. So this was developed in the context of the database community. And the key characteristic here is that I have transactions. Right? The idea of a transaction is the following. You can actually encapsulate a sequence of requests, right, depending on what the object does. If I go back to my file server, if I had a transactional file server, then I could say, okay, I'm going to start a transaction and I'm going to submit several requests to read this file, to write some other files. And once I finish this transaction, I want all these operations that I submitted within the scope of my transaction to be atomic. Which basically means either they are all executed or none of the operations is executed. Right? So the main difference here is really the notion of atomicity. Well, it turns out, and also the consistency criteria, which I will discuss later. But it turns out that these small differences, they make a big difference in terms of the protocols that you actually can come up with. So let me illustrate a little bit something that I believe doesn't really deserve a lot of explanation because I suppose everybody believes this. So object replication, the main goal for studying object replication was fault tolerance. If I have my file server and I have two clients connected to this file server, and let's assume that here the single box means there is a single server running this, single machine running this file server. If the machine crashes, the clients don't do anything. They have to wait until the machine recovers, right? So if I translate this to the internet, for example, if you're running some service, your client is going to be your HTTP, your browser, for example, sends a request to some remote server. If this server runs in a single node and for some reason the node crashes, you don't get your request is executed. So the simple solution to this is to create replicas of this server. The idea here is that if one of these nodes crashes, you can still have the requests executed by the other servers. And you have to do this you have to be smart in the way you implement this so that it becomes transparent to the clients, right? The other thing is you may want to place these file servers in different networks or in different rooms so that if, for example, I don't know, one room burns, you don't lose all their servers. But the idea is to have redundancy so that if some of the servers crash, you can still keep going with the other ones. So that's the main idea. I guess simple. The main thing here to keep in mind is the main motivation for this research in the context of object replication was fault tolerance. Now, if you look at databases, obviously fault tolerance is something important too, right? Maybe your internet service depends on some remote database. So if that server crashes, you still want your service to continue executing, so you replicate the database. But in addition to fault tolerance, which some people also call high availability, we also want to have good performance. So the idea of good performance is the following. I had two clients. I added some database servers to be fault tolerant, but now, since I have more machines, right, I also want to have more clients connected to my machines. In addition to having this fault tolerance, I also want to serve 6 clients as opposed to my original 2 clients. So the idea of also doing replication for performance was part of the main motivation for database replication. And as you're going to see, some of the protocols that can solve one of the problems, namely fault tolerance, they may not give you better performance. They may not give you scalability. So this is, performance here can also mean scalability in the sense that by adding more servers, I can serve more clients. Some of the protocols that give you one may not give you the other one. And this is going to become more clear, I hope, in the continuation of the talk. Okay, so let's review what I just said. We are interested here in object versus database replication, right? And these two areas, they have different goals. One is targeting mainly fault tolerance. The other one is targeting both fault tolerance and performance, or scalability, if you will. They have different models. I went very quickly here. I have to tell you more because, as some of you asked already, it's not too clear what databases mean. I'm going to go more in detail. But from now, we can see that there is already a difference between these two models. One targets objects which are non-transactional, and the other one has the notion of transactions inherent to the databases. And it turns out, maybe not so surprisingly, that there are different algorithms for these two areas of replication. So again, to a certain extent, the goal of this talk is to show you that these algorithms, they're not so different, or they don't have to be so different. Now, in some of this, what I plan to do next is to tell you about some of the protocols. And to simplify the presentation, there are many protocols, as you can imagine. So research on replication started, as I said, about 30 years ago, the first protocols. And as you can imagine, there are many, many proposals, right? There are different protocols solving different problems, sometimes solving the same problem. And to make the presentation a little simpler, and I don't have time to go through so many protocols, I'm going to target on a class of protocols for replication that is based on group communication. For all those who attended my talk 2 years ago, I spent some time talking about group communication. I will be very brief this time. But I still have to give you some information about what this group communication is, otherwise you won't understand the protocols. So what I mean by group communication is that messages are addressed to a group of nodes, as opposed to point-to-point messages, which I send a message to a specific node. I can send a message to a group of nodes. And I can address this group of nodes as a single identifier. Okay? So here in this picture I have 3 nodes. On the left side I have an example of point-to-point communication. Notice that the arrows, they mean a message is being sent from one node to the other node. And since this is point-to-point communication, if node 1 wants to send a message to nodes 2 and 3, it must send 2 messages. On the other side, I have group communication. By means of some protocol that I will not discuss here, all these 3 nodes, they agreed to be part of the same group. So whenever one of the nodes wants to send a message to the group, it simply says, send a message to this group ID, and then the message gets magically delivered to all of them. So in fact, there is no magic going on. You have to implement this functionality here by using whatever your underlying model gives you. And usually what the underlying model gives you is point-to-point communication. By underlying model, I mean TCP, for example, or UDP, depends on how you're building your system. But for the programmer, it makes a big difference, right? Because the level of abstraction here is much higher. I don't have to send the message to one node after the other. I simply send a message to the whole group. So my replication protocols, they are going to use a group communication that gives us this, and also gives us a little bit more that I will detail later. Because it gives stronger properties for my communication system. Okay, now what I'll do is I will tell you a little bit about the replication model for each one of the two contexts that I'm discussing here. I will try to be as simple as possible. I don't want to introduce complex object and database models, because if the models are too complex for a relatively short presentation, you may get lost in the specifics of the model and miss the bigger picture, which is to compare these two algorithms, these two classes of algorithms. So my object model here is as simple as I can imagine it. There are clients. These are the entities that submit requests, and they are servers, which are the ones that store my objects. The object can be whatever. It can be a variable, for example. The object, if the object is a variable X, so the servers, they store copies of X, and the clients, they can submit requests to inspect the value of X or to change its value. And I'm going to restrict my operations to two kinds. I can do a read operation and I can do a write operation on the object. A read operation returns the value of the object. So if my object is X, the clients can issue a read, and then they are going to receive from the servers the value of X. And they can also do a write. So a write has two parameters: the ID of the object, X, and the value that the client wants to assign to X. So write XV updates the value of X with V, and then returns an acknowledgement. So that's pretty much my model. Yes?
Is it important that read does not result in any exclusive acknowledgement?
So the read returns the value of the object, and implicitly you can assume that this is an acknowledgement. You send the read, and then you get the value of the object. So when you get the value from the server, or you don't, right? Or you don't. Yes. But it's the same for the write. You send the write, you get an acknowledgement, or you don't, right? So that's the model. It's quite simple. But it's not enough to discuss replication protocols, because it doesn't tell you much about the correctness of my system. So if I simply tell you, build a system that does this, right? And if I would ask each one of you to build a system that does this, there are some fairly good chances that there would be as many different systems as the number of people here. I'm not saying anything about the behavior, how this operation should, how the object should behave. If multiple clients, for example, they start accessing my objects, I have to be more precise with respect to my consistency. So what I expect from these objects, what behaviors are correct, which behaviors are not correct. So defining these rules that define that specify the correctness of the object is what it's known as consistency criteria. So it's very simple. It turns out that it can be quite simple for if my system has a single client and has a single server. But it becomes more complicated if I have more general cases. Like, for example, I have multiple clients that can now simultaneously send requests to my objects. And if I have multiple servers storing the object, which is basically the goal here, right, is to replicate the servers storing the objects. And I can even make this more complicated by assuming that some of the servers, they can fail. And that's precisely what we are going to do. But we are going to do this in steps, so that we can first understand what it means in each one of these cases until we reach the most complex one, which is the last one. So, very intuitively, let's define the consistency criteria for my system. And in the simplest case that we have, there is a single client in the system, there is a single server, and there are no failures. Okay? In addition to the things I told you before. My object is X, and there are two operations, read and write. So there are two. So the way I'm gonna go through this is by showing diagrams like this. So these are basically, they show you the agents, the parts of the system that can issue operations. There is one client, there is one server, and then the two arrows, they show the operations that were executed by the clients over time. So time grows to the right. Okay. So if I look at the execution of the client, so the client line, it means that the client issued a write operation, write x1. So this basically means the client wants to change the value of x and assign it value 1, whatever value it had before. And as I said before, it receives an acknowledgement once the server has done whatever it takes to execute this operation. Later, the client issues a read operation, which is going to return the value of x. And then eventually it receives the current value of x. So if there is a single client, right, there is a single server, if you execute a write, if you change the value of x to 1, and later you read the value of x, I hope everybody agrees with me that you expect to see the new value that you wrote, right? Does anyone disagree with this? Okay, so that's the first step. This can be implemented in many different ways. Okay, and it turns out that I don't need to introduce the server into the picture to discuss consistency criteria, but I will do so because I think it's more intuitive. So I'm going to show you one implementation of these operations here that in reality gives the expected behavior. So this implementation means I'm going to show you what the server is doing, right? So the server is sitting, waiting for a request. Eventually, one request arrives from the client, the very first arrow here. And this request says the client wants to change the value of x. So x had some initial value that I'm assuming to be 0. And as soon as the server receives the request, it does some internal processing, which in this case here is something really simple. It may just be assigning the value 1 to the object x. It changes the value of x and then sends a reply back. So when it sends this reply, basically this reply means I completed the operation. So the variable x or object x has changed its state. The client receives the acknowledgement. It knows that this operation has been performed. Now, this gives the guarantee to the client that the write was successful. It changed the value of x. So if later the client issues a read, the client is going to receive it, is going to return the answer, and so the server is going to read the current value of x and return it to the client. Okay? So in this simple case here, and in the kind of objects we are looking at, I guess there is no doubt how this should behave, right? But this very quickly becomes much more complicated. Do you want to see why? Let's consider a slightly more complicated system. I have two clients now and two servers, right? And the servers, each one has a copy of X. Now the first client, it issues the same operation as before. It issues a write operation. It eventually gets an acknowledgement. So it knows that this operation here has been completed. Now, let's see how this could be implemented. There are many different ways to implement this. Let me show you one way to implement it. So the way I implement this is, the client chooses, so this you can assume that whatever goes in this box here is some library that implements, that's going to help me with my implementation. So it selects one of the servers and sends the request to one of the servers. So the server receives it, changes the value of X, and then forwards the new value to the other server. Okay? Sends the value to the other server. And I'm not making any assumption about the time it takes for messages to arrive. It can take some time, can take longer time for this message here to arrive. But as soon as the message arrives at S2 changes the value of X. So this is a reasonable implementation for my write. Okay? Now, what happens if the other client issues a read operation? So this client here issues a read operation, X, and so the implementation of read X is, I choose one of the servers, I send the read request to the server receives it and returns the value of X, the current value of X. is going to be 0. Okay? So later on, the client issues another read operation for the same variable, the same procedure, choose one server, happens to be the same here, which returns the current value, it returns 1. Now, the question I have for you, is this implementation correct? So does anyone think that it's correct?
Provide the criteria so it may be counted correct just because there are no restrictions in our model.
Right. So the answer is it depends. Right. We don't know enough to tell whether this is correct or not. It may not be intuitive, or for some of you it may be intuitive, for others it may not be intuitive. But I cannot tell whether this is correct or this is wrong because we don't have enough information. So in reality, we don't have. You can think of consistency criteria as a contract between the system, right, the servers, and the clients. I haven't showed the contract yet, so you cannot tell me that this implementation here is violating the contract because it's not clear where it is, right? And it turns out that it may be correct or may be incorrect. Well, how can you actually tell whether it's correct or not? Oh, one more thing, very important actually. In reality, to tell whether this implementation is correct or not, I don't have to even look at the servers. So for a while, let's just remove the servers from the pictures, and let's look only at the behavior of the clients. Right? What I did from the previous slide, I simply removed what happened in the servers. I'm just looking at what the clients see. Because in the end, that's what matters. Right? The clients are interested in what they see as their values, not at what happens in the servers. So I'm going to define my consistency criteria only by looking at what happens at the clients. Well, we are going to look at two consistency criteria. The first one is called linearizability, and the second one is called sequential consistency. There are others, but we are going to concentrate on these two, are the most used ones. So let me ask you this. Has anyone ever heard of this consistency criteria here? Okay, cool. That's a fairly large number. So let's look at the first one, linearizability. And I'm going to do this in a very intuitive manner. I'm not going to be too strict about this definition. So a concurrent execution is said to be linearizable if there is some sequential way to reorder the client's operations. Right? I can actually play with the operations as they should by the clients. But I must respect two properties. The first one is that whatever sequential order I find for these operations, it must respect the semantics of my objects. Okay? This basically means that if I issue a read after a write, the read must see the value of the write. The other constraint is that I can play with the order of these operations as long as I respect the order of no-overlapping operations. So the notion of overlapping here is with respect to real time, right? If two operations are like this, so they overlap in time, it basically means that one operation starts before the other one finished, and as issued by any clients, right? Overlapping two operations issued by any clients. If there is this overlapping with respect to real time, then I can reorder my operations. But if they don't overlap, right? If one finishes before the other starts in real time, I cannot reorder them in order to build my sequential execution. So let's see how it works. In reality, it's not so complicated intuitively. So here is what happened to my system before: the two clients and the values that return. So the game here is the following: I have to find some sequential execution. I have to totally order my operations, right? I have to place them over the same line so that they respect the semantics of my objects, and so that I don't violate my non-overlapping operations. So let's try to place the operations over the single line and see what happens. So this would be perhaps the most obvious way to place these operations over a single line. So I have a write issued by the first client, finished, then the second client issued a read, and finished. So the value returned here is 0, right? But the previous operation changed the value of x. So is this fine? with respect to serializability? It's not, right? Because it's violating my previous write operation. So if I'm trying to prove that, to convince you that this execution here is linearizable, I have to do better than this case. So let's try to address this issue. And to address this issue, what I can do is I can swap, basically. I can swap my two operations. I have to place this read before the write. Because the read returns 0, right? So it cannot take place in my sequential execution. It cannot take place after the write. It must take place before the write. So in this case here, the semantics of the object is respected. Because the first read is returning 0, which was the initial value. And then I have a write that returns 1. And then I have a read that returns 1. I have a write that updates to 1. And then I have a read that returns 1. Here is fine, with respect to the semantics of the object. But the problem here is... Who tells me what the problem here is? Well, let me ask you in a different way. If I give you this sequential execution, would you be convinced that this concurrent execution here is linearizable?
Maybe you can't just swap the non-overlapping.
Yes, I cannot swap no overlapping operations. These two operations here, they don't overlap. This one here started after this one here finished. And in this execution, I had to swap them, so I'm violating the second constraint. Let me go back to the constraint so that you guys can... So the constraints say that I should respect the semantics of the objects, and I should respect the order of non-overlapping operations, right? So this case here is problematic. I can tell you, it's not linearizable. There is no way I can find a sequential execution that's going to respect both constraints. So our first attempt violated the semantics of the object, and our second attempt violated the non-overlapping order of operations. So it turns out that there's no way I can find a sequential execution. What this means is that this concurrent execution here is not linearizable. If you had a contract with the service provider saying that every execution that your clients are going to see is linearizable, here is a proof that the service provider broke the contract. It produced some execution that is not linearizable. Is that fine? So here's a slightly changed version of my execution. So it's pretty similar, but the difference is that this client here started the operation a little bit before. Actually, it issued the read operation before the write was completed. Now, these two operations, they overlap. And if they overlap, now I have the freedom to choose the order, their corresponding order. And if I do something like this, then I'm fine. So if I look at the results of the operations, there was a read that returns 0, fine. Then here we changed the value of x, and then later we read x, and it was okay. Well, I had to swap the first write with the first read, but that's okay. So this execution here, if that's the execution that my system provides me, this one here is linearizable. Okay? Is it clear so far? Yep. So when does this finish? It's 7, until 7 or 6:30? 6:30, I guess, right? Mm-hmm. So let's look at the other consistency criterion that we are going to consider here. It's called sequential consistency. The wording is very similar to linearizability. In reality, it's almost the same with one small exception. A concurrent execution is sequentially consistent if there is a sequential way to reorder the client operations such that it respects the semantics of the objects as determined by their sequential specs, and it respects the order of operations at the client that issued the operation. What's the difference to the previous one?
You can change operations from different clients.
Yes. So I can swap operations that are no overlapping as long as they are issued by different clients. I cannot reorder operations issued by the same client. So is this stronger or weaker than linearizability? It's weaker. So what does that mean? What does it mean to be weaker? So, as someone rightly said, sequential consistency is weaker than linearizability. So I'm asking, what does it mean for a...
Each linearizable system is, we can achieve sequential consistency and
not the other way around. So any system that is linearizable is also sequentially consistent, but not the other way around. So let me prove this. So here is our very first example, right? It must be familiar to you now. One client writes X with 1, the other client reads X and returns 0. So is this execution here sequentially consistent? Yes. It is, because all it takes to get a sequential execution is to do this. I'm not reversing the order of any operation issued by the same client, so it's okay. I can actually do it, right? So this is the case that shows that sequential consistency is weaker than linearizability. This execution here is not linearizable, but it is sequentially consistent. So as homework, you have to show that any execution that is linearizable is also sequentially consistent. What about this case? So the difference here is slight. The difference from the previous case, I only changed the value that my second read operation is returning. Now it's returning a 0. It's not returning 1 anymore. So is this execution still sequentially consistent? No. Okay, I guess you guys all got it. You cannot swap the operations that come from the same client. Okay?
It depends actually. It's not consistent as long as we are sure that there are new clients.
Say it again.
It's only not consistent as long as we are sure that there are no other clients.
no, it's very symmetric.
No, the first, even if I have a single client here, it would break the consistency already, because the read is returning 0. It cannot return 0.
Broke sequential consistency.
Yes.
There was, for example, client 6 and it's writing yes 0 to the S.
If you have another client? No, but it doesn't matter. You can even remove client 2 here. By just looking at client 1, it...
Removing clients does not actually any clients does.
But I have to change the operations too, right? I have to issue some operation that writes 0. Well, but that's a different. I don't have to add another client. If I add an operation here that changes the value of writes X 0, that would make it. But as it stands, it cannot be. It violates sequential consistency. Now, what does this do? Okay, well, just a few attempts to show you that there's no way you can actually achieve sequential consistency. But I guess everyone understood what this is, so I'm going to skip this. Okay, so that's it for the object replication model. Now, let's have a look at the database model, because let me remind you that the goal here is to compare database replication to object replication. So I have to start with the first things first. First, the model for each one of them, right? Understand how the models are different, or maybe not so different, and what consistency criteria each one of these models has. So we saw it for objects. Now let's have a look at databases. And since the goal here is to compare these two contexts, I try to define a database model that resembles as much as possible my object model. So this means, just like before, I have clients and I have servers, right? Now the operations, they have to be a little, the set of operations a little richer, because I have to capture the idea of transactions. So in addition to my read and my write, I also have a commit and an abort operation. So the idea here is the following. A client starts issuing reads and writes, and eventually it says commit. When it says commit, all these operations should actually happen atomically, Either they all happen or none of them happens. If after issuing a number of operations the client says abort, it's as if none of the operations had taken place, right? They are removed from my system. We are going to concentrate here on committed executions. So implicitly, I'm assuming that a sequence of reads and writes, they are followed by a commit, okay? So the other difference is basically the notion of a transaction. A group of read and write operations, which is followed by a commit or an abort operation. That's the idea of a transaction. And in transactions, they have special properties, which have been named ACID properties. So ACID because it stands for the 4 properties that are assigned to transactions. The first one is atomicity. So we're not interested in all of these properties here because they make sense in different contexts. But we are interested in some of them. Yes?
Does your model imply that transaction beginning is implicit?
Yes, our beginning of the transaction is implicit.
No nested transactions?
No nested transactions, just plain transactions. And as you're going to see, it's going to be the examples are going to be very simple because I don't have to look at complicated examples to show to contrast the two models. So the first property from the ACID set of properties, it matters to us, is the notion of atomicity. So I have been insisting on this property. Either all the operations of the transaction, they are executed, or none of the operations are executed. The second one is not so important for us. It says that a transaction, if it sees a database in a consistent state, and consistency here means a set of properties that are assigned to the database, is not going to lead the database to an inconsistent state. It doesn't matter for us. Consistency here, it means it consists in a different sense. Integrity constraints for those that it means something. The other one is isolation. This is the property that really matters to us because this is the property that's going to define what I've been meaning by consistency. And in the particular database isolation that we're going to consider is called serializability. It's probably the best known consistency criteria for databases. But it's not the only one, but it's the best known. For all those of you who have maybe have worked with database, you may realize that a pretty common property for database these days is snapshot isolation. Main database, they provide you this, which is not serializability. Right? So we're going to consider serializability. And the final property is durability. It basically means that once a transaction has been committed, no matter what happens to the system, it will not lose the transaction. Okay, so it's not relevant. It's not too much relevant to our context either. So let's look at serializability. This is what we're going to use to compare to the other properties that we saw for objects. So a concurrent execution is serializable if it is equivalent, here loosely speaking, to a serial execution with the same transactions. Okay, so I have a concurrent execution with transactions. Now I say that this execution here is serializable. Sometimes I may also say that it is one copy serializable if it is equivalent to some other execution where all transactions happen in a serial way, one after the other. I have to be more precise with the notion of equivalence, otherwise it doesn't mean anything. So two executions are equivalent, or more precisely, they are view equivalent if they have the following two properties. Their transactions, they preserve the same reads from relationships. So this basically, reads from means that a transaction reads a data item. So you're comparing two executions. If a transaction reads a data item in one execution, it reads the same from another transaction. It reads the data item from the same transaction in the other execution. Okay. So in other words, if a read takes place, so transaction T reads the value X that transaction T prime changed in the concurrent execution. In the serial execution, transaction T must read the value from transaction T prime. Okay. In the execution, they have the same final writes. So the most important property here is the first one. So two executions are equivalent. Most important property in our context. Two executions are view equivalent if they have the same reads from relationships. Okay. So our pictures now are going to be changed a little bit because I have to account for transactions. Before I didn't have transactions. Each operation was complete in itself. So now I have to somehow represent transactions here. And the way I'm going to do this is by connecting the operations. So the thin bar, it means that the first operation is connected to the second one, and this makes a transaction, right? If there is no, if there is a single operation, then the single operation is also happens to be a transaction. So in this picture here, client C1 issued a transaction that does write X1, and then does a read of the value X. And the second client issued a single transaction that reads the value of X. Okay? So the question here is this execution here serializable? And the game now is, I have to find some sequential execution. I have to swap my transactions, but I have to swap them as transactions, not as operations, right? I have to take the first transaction here, and then place in my sequence execution, take the second transaction, and see whether there is a place where I can position the second transaction, so that in the two executions, in the concurrent one and in the sequential one, they respect the reads from relationship. So let's try one way. Let's place them like this, right? In this execution here, this transaction, the second transaction read 0, right? So notice that it didn't see the value that the first transaction wrote. First transaction wrote X1, and this operation finished. But this transaction here saw a 0. And I'm trying to use this sequential execution here to try to convince you that the concurrent execution, the one on the top, is serializable. Are you convinced? It seems. That's, so I found some sequential execution. If I look at the values that are returned here, they seem plausible. Do they respect the reads from relationship? Well, this transaction here, I'm placing it before transaction C1, right? In order for this transaction to return 0, because if I place it after the transaction of C1, then it should return the value of 1. But if I place it before, then it can return the initial value. Oh, can I swap the transactions in this way? I can, because the second transaction didn't read anything that was written by the first transaction. So this execution here is fine. It happens to be serializable. So do you guys remember when I told you about the objects? There was some, forget this bar here, and if you reason about the consistency criteria for objects, we saw that the execution that resembles this one here, it was sequentially consistent, but it was not linearizable. Remember that?
Reiterate the reads from relationship.
Yeah. So reads from means that I can reorder the transactions as long. So in the two executions are going to be equivalent if the transaction in this execution here reads from the same transaction that this one here read. So this transaction here, it read from some T0 that initialized the database, right? So why am I saying that? Because it read value 0. So it did not read from transaction T1. So it read from some T0. So in this execution here, the transaction issued by client 2 does not read from transaction issued by client 1. So they're equivalent. So it's serializable. So what about this execution here? Is it serializable? Excuse me? It's not serializable. So let's see if I can place. So notice that the first transaction, right, it does not overlap with the second one. So if you go to the previous execution, so they did overlap. So here, and then I found this. So here they don't overlap. Right? So what do I have to do to make sure that the values returned here, they are correct in the sequential execution? I have to place my second transaction before the first, right? In the sequential execution. So is this a proof that the previous execution is serializable?
Maybe we swap it.
Yes, we have to swap the two transactions. Is this a problem? It's not a problem. Actually, if you go back to the serializability definition, right, it doesn't say anything about swapping no-overlapping transactions. It just says that two executions are, so an execution is serializable if it is equivalent to some sequential execution. And my sequential execution can be anything as long as it respects the reads-from relationship. So I can actually do this. It's quite surprising, right, that serializability allows me to do things like this. But it does allow me to do this. So what about something like this? Now I moved up my transaction to the first client. Now the first transaction changed the value of x, and then the reads x, and the second transaction, so this is a different transaction, issued by the same client. It read x. Is this execution now serializable? Does anyone think it is serializable? So I'm sorry to tell you. Oh, there was one hand there. So I'm sorry to tell you, but this execution is also serializable. Serializability doesn't say anything about particular clients. Actually, if you go back to the definition, it doesn't even mention the client. It only mentions transactions, right? It doesn't say anything about the clients. Yes?
But then the property of durability in terms of transactions, what would it mean?
Yes, that's a good question. So, yes, we'll look at serializability only. But maybe depending on how you define durability, you would rule out this property. But if you only look at serializability, right, it allows a definition, an execution like this. Now, you may be wondering, so everything is allowed by serializability. Is there something that's not allowed by serializability? Can you guys give me an execution that's not allowed by serializability?
Right, x1, and the right read zeros.
So, I guess, if I understood you correctly, let's look at this execution. So the first client does a write. So there are a few things to note here. The first one is I'm using now two variables, right? X and Y. So my database now grew. There are two variables in the database, X and Y. The first transaction changes the value of X, assigns it 1, and then reads the value of Y. The second transaction writes the value of Y and reads the value of X in the way shown in the picture. Now I have to look for some serial execution where I can place these two transactions one after the other, right? So let's do it by trial and error. I don't have it. So let's imagine that you place the first transaction, the transaction issued by client C1 before the transaction issued by client 2. So the problem here is that the first transaction, it changed the value of X, assigned it value 1. In the second transaction, it read value of X 0. So I cannot place the second transaction, the C2's transaction, after C1's transaction. Is that clear? And I cannot do the other way around either, because then the problem is variable wide. So there's no way to reorder these transactions that's going to make the semantics appropriate. So it turns out that it's not serializable. Okay. Well, anyway, so how do these consistency criteria they compare? It's very hard to compare these consistency criteria because they are for different models, right? So if they're for different models, how can I compare these things? So let me do a little bit of stretch a little bit this what I'm going to say in order to try to compare these three consistency criteria. And let's assume that in my database model, I only have single operation transactions. Every transaction has a single operation. Otherwise, it's difficult to compare. Now, if I do that, so here's what I have. I have the two consistency criteria for objects and one consistency criterion for databases. So is serializability in this simplified model equivalent to any one of these consistency criteria that you saw before? It's not. But it turns out that there are variations. So I can add some constraints to my serializability so that they become equivalent. And this has been done in the past. So there is something called strong serializability, which is serializability as we saw, and on top of it we say we cannot reorder non-overlapping transactions. Right? If you do that, and your transactions are single operations, then you end up with linearizability. And there is also something that is so this is not very used in practice. I don't know any database that gives that, because it turns out that, as we're going to see in the continuation of this our discussion, it's very expensive to implement linearizability, and it's very expensive to implement strong serializability too. Now there is something else that some database give us, which is called session serializability. And here, session is something that has to be better defined. But you can imagine a session as something that is issued by the same client. So session serializability is like serializability, and in addition to it, I also say that if transactions are issued in the same session, then one transaction should see the change made by the previous transaction. Turns out that this is equivalent sequential consistency. Now, is there in the scope of objects anything that is equivalent to serializability in a model with single operations? Not that I know. And if you think a little bit about it, it becomes a little bit pointless, right? Because if my operations are, if my transactions are single operations, and I can reorder them in any way I want, I may defer all the reads to the very beginning of the operation so that they will never see any writes that happen in my system. So it's a little bit meaningless. So that's maybe to explain why it has not been defined in the context of objects. Okay, so what's going to happen next is I will concentrate on two criteria. One for objects and the other one for databases. And as you can see, they are not really even slightly comparable. But I hope that by showing you how to implement this one here in the context of objects, I give you an idea of how expensive it is to get this guarantee, and why serializability actually allows us more efficient implementations. Okay. Well, in addition, that's the consistency criterion that has been used for databases. So this represents the typical replication protocols that were proposed for database replication. Okay. So I have a few, I can illustrate here what it means to be serializable, but not session serializable. For example, in this execution here, I have a second transaction that reads a value that precedes that doesn't see what the previous transaction did, right? And I can reorder them like this to have a sequential execution. So this execution here is serializable, but it's not session serializable, because as I said, I cannot in session, if I have a session serializability, I cannot reorder transactions from the same clients. Okay. So if my system gives me session serializability, this will not be allowed. And it's quite intuitive, right? If I execute my transaction against a database, I'd like any future transaction that I executed to see my previous transaction. And here's an example of a system that gives session serializability, but does not give strong serializability. So the transactions T1 and T2 that were issued by client C1, transaction T2 saw the writes that were performed by transaction T1. Now there was a transaction 3 that was issued by different clients which did not see the writes, but I'm free to reorder them. So that would be an example, just to illustrate what I said before. And finally, this is an execution that is strongly serializable. The two read-only transactions, they see the values of the writes. Okay. So I think I'm gonna stop here, because it's a nice makes a nice break to the continuation. What I will tell you about tomorrow is how to implement this consistency criteria, right? And the way I'm gonna do this is by first showing typical replication models for objects, and then a new replication mechanism that's gonna make object replication closer to database replication. And I hope that by looking at these different protocols, I'm going to understand intuitively why it's so expensive to get linearizability, and why it becomes cheaper to get serializability. Okay? So thanks for your attention. I hope to see as many people tomorrow.